At the first virtual Ifac World Congress, all plenaries and semi-plenaries are accompanied by an entertaining live element. This presentation is followed by a live panel discussion where experts in the field recapitulate and debate on related ideas, questions, and open problems.
You're live.
Hi, everybody. Welcome to the panel discussion, Can we accelerate the impact of systems and control? We have an exciting set of panelists here assembled, and I'd like to introduce them all to you. So Danny Abramovich from Agilent Technologies, he's a systems architect in the mass spectrometer division. By day, he tries to apply systems theory to building smarter analytical instruments, while by night, he tries to use what the devices tell him to correct his understanding of systems theory. Welcome, Danny. Kira Barton, she's an associate professor in the Mechanical Engineering Department and Robotics Institute in the University of Michigan. Her research focuses on modeling and control for advanced manufacturing and robotic systems. Welcome, Kira. Angelica Pier is a full professor at the Free University of Bolzano in Italy. Her research focuses on systems with humans in the loop and brings together knowledge from multiple disciplines like robotics control and human system interaction. Last but most certainly not least, Martin Steinbuch. You just heard his plenary. He holds the chair of systems and control at Eindhoven University of Technology, where he is distinguished university professor. He's a high-tech systems scientist, entrepreneur, and communicator. I'm Anu Anuswamy. I'm at MIT in the Department of Mechanical Engineering, president of IEEE Control Systems Society, and it's a pleasure to have you all here with us. So without further ado, I'd like to start off with a question to Martin, and to get going with that, could I request that you played that the clip?
Get those wonderful toys.
Exactly. So Martin, here's a question for you. Where do you get those wonderful toys?
Yeah, thank you for the clip, and thank you on my behalf also the other panelists to be here with us. So of course we built ourselves a lot of the things I showed in my semi-plenary lecture, but also we got a lot of nice setups from the surrounding industries. When I started the lab about 20 years ago, I said I want to get rid of those inverted pendula systems because I want my students to really feel what real systems, how they behave and what they have as problems. And that's the reason I was all the time asking the industries around us, hey, please give me your setups which you feel would be useful for us to have in the lab. So I'm very fortunate with that, but also we have a great workshop where we can actually build our soccer playing robots, our medical robots ourselves, and that's also joyful to work with.
Wonderful. That's absolutely wonderful. So I want to go to your plenary, and interestingly enough, you had 3 different nonlinear time varying controllers: LPV and SPAN and Higgs, and they have interesting commonalities. As Danny pointed this out, and absolutely true. They all seem to have like PID type of control actions, and they all seem to have physical parameterization, and that seems to be a common thread. Is there a general lesson here?
Well, first of all, I was teach, of course, like many of us, with a lot of state space and theories. And when I came into practice in Philips in the late 80s, working on CD players, I was realizing myself, hey, to stabilize a system which for small signals at least is behaving linear, to stabilize that, you simply have to obey the Nyquist criterion, and you simply have to utilize PID-like structures. A basic double integrator is only stabilizable with a differential action, and then a PD controller is the most simple you do. So most of the systems I've been working with are in their nature more or less linearly behaving, at least for small signals, and then for single input, single output, it's trivial that close to the bandwidth you need a PID-like structure. Outside the bandwidth, you can do fancy things. And this all holds for the feedback, not for the feed forward. And with feed forward, we can do many other nice things, which we also showed, I think, in the video. And the combination with nonlinear controllers, I really like that. But in the essence, you have to stabilize the system with first linear thinking, and then you add creative nonlinear things to really improve performance. But stability is the first thing you have to handle.
So that makes a lot of sense. That makes complete sense. I want to go to the next question. So you talked about personal robotics, and all of the different features that you're talking about are really very compelling. And this is a question that I often get from my colleagues who are not in control. Like, the moment you start to open up these windows of sensing and communication, safety and security aspects really become important, right? And how do I keep my robots from being hacked? And so is that something that you really have to, does it keep you up at night?
Not really, no, because I believe that people can solve this. I'm not a security person, so other people should at least think about this. However, safety, of course, is crucial in all the steps you do, especially if you want to bring things also to the market. So especially, for instance, the surgical robotics, by design, we think about safety measures. Also, various layers of the control loops are important there. And in our group, we basically also do work on supervisory control algorithms, where you have monitoring systems for safety reasons. But security, that's a different ball game, and that's not my discipline. But I believe that others can solve that using also, again, the law of more, because computing power will be smarter and smarter, and hence also the dedicated chips we can have and can develop for security.
I'd like to invite others to weigh in. Danny, do you see, so what's your take on this? Do you think that the security aspect is something that's really important?
I think it is important, but as Martin says, there are other people who will, other engineers who will take care, who will be responsible for that, not us. But it's important for us to impose that. It's one thing when your computer, crashes because somebody put a virus on it. It's another thing when your personal robot is cutting your hair and, it cuts off your ear instead because somebody hacked it. And for me, this is not the robot part of it, but I still have this vivid memory of going to get my hair cut. My father used to find these cheap barbers, right? And I go to get my hair cut when I was about 10, and the gentleman who was doing it, his hand shook visibly, right? So for 10 minutes, I'm in terror as this guy is like using scissors behind my head. And at the end of it, he goes, "Would you like me to shave the back of your neck?" And I'm like, "No, I'm good," right? And so we have to have, we can't, we can't have that kind of an experience with mass-produced robots, right? And I think that there's a safety has to be built in that way, and devices that can't be individually tuned by a bunch of engineers. So surgical robot, a bunch of people can take it, can make sure that one's working. But when it's a $50 personal robot, you're not shipping an engineer with each one of them, as they say. So I think that those are issues that we need to think about.
Absolutely, absolutely. Kira, I was wondering what your thoughts are on the subject.
Well, I definitely agree with both what Martin and Danny are saying, and I think one of the things, you know, sort of from the control side that we have as a tool are, you know, these ideas of observing what's going on, and then, you know, I do a lot of work in the manufacturing domain, and a lot of the ways that we try to think about how to at least identify when something might be going wrong is through, you know, tools like digital twins. And so some of these ideas of can you have, you know, systems that are set up where you're able to monitor and be predicting, you know, what you expect to be happening, so that you can sort of preemptively start to identify if something's going wrong, or you have behaviors, or you have data that's coming in that maybe shouldn't be, or doesn't look quite right. You know, I definitely wouldn't want the experience that Danny's talking about from a robot cutting my hair, but I think that you know, some of these ideas of, you know, being able to sort of have expectations of what you want the systems to be doing, and then observing that is maybe one way to think about bringing security in conjunction with, of course, you know, all of the sort of tools and techniques that are being developed in the computer science side of things right now.
That makes complete sense. I mean, we are indeed, after all, in the business of observing and estimating and predicting and MPC. And so all of that we should be able to bring to bear on anything like cyber attacks, which could be viewed as a disturbance, you know, very active and adversarial disturbance, no doubt, but should certainly our community is very well poised to address this problem, I think. Angelica, I'd love to hear your take on it.
Yeah, I think what we have to take care about is that robotics typically implies to have different kind of layers. So we start, let's say, with the lowest layer where we have low-level controllers to move the individual limbs, joints, and so on. But then we have also the higher levels, you know, so where we have different kind of behavior that we need to control. And so essentially we need to look at the problem of safety on all of these different layers. So starting from the really low one, so we are used in control, but also the higher ones, you know, that tackle the behavior. And especially when it comes then to robots that interact also with humans, with people. So I would like to come back to what we just heard before, namely the word expectation, prediction, and so on. So here it is very important, let's say, that the behavior is also predictable, so that humans actually can understand what is going to be the next step, so to also render the whole interaction also more safe. And I think what we are supposed to come up with is a holistic framework, let's say, that brings together all these different layers in a one single framework, so that can handle safety on all of these different layers.
Yeah, absolutely. I really like the idea. So I think having that hierarchical structure and learning, have the higher layers provide more cognitive levels of oversight, I think is a great idea. Thank you. So I'd like to now go to the next one, which is also something, Martin, that you brought out in a very compelling and dramatic way in your plenary, is Moore's Law. So there are so many different technologies that Moore's Law focuses on, and you mentioned many of them. So what aspects of Moore's Law are most critical, do you think, for advancing dynamics and feedback systems? So I'd like to address this question to Martin first, and then to all the panelists. Martin?
Yeah, there are, of course, two ways of an interpretation of this question. So what will technology mean for dynamics and feedback systems? But you can also say, okay, what part of our discipline is relevant to make sure that Moore's Law goes on?
Yep.
So the first question is the impact. I think Internet of Things and sensors everywhere will be the biggest one. So we will have an abundance of sensors. And of course, to measure is to know. So reducing measurement noise is one of the key things we can utilize in an abundance of having sensors. At the same time, there will be a lot of sensors which are cheap and which are not reliable. So I think sensor technology and integrating that into our feedback control systems. That is, I think, for me, one of the challenges of the next decade. Of course, on top of the standard things like distributed control, utilizing networks, etc. Those are the things which are already mentioned often. Now, the other is also interesting. How can our profession and discipline help to actually make sure that Moore's law goes on? Because it's not trivial. It's not a law of physics. It's a law of description of things which are happening, which are a result basically of our profession. Without dynamic and feedback systems, without our profession, ASML is not able to increase its performance. And henceforth, the law of Moore will stop if we stop training our PhD students with the level we do currently. So I think our profession is crucial in really pushing the limits of performance, in going deeper than the nanometers. And we need there all the things we are currently doing with advanced identification, combination with controls, data, learning, all the things we currently do with our discipline are crucial to still make high-tech machines which are able to make those wonderful chips in all our phones and our electronic devices.
I think that's a great tagline. We really need controls in order to keep Moore's law going.
Absolutely.
It's a great mantra for us to keep in mind. Danny,
Yeah.
what are your thoughts?
So I agree completely. I think that there's Moore's law as an enabler. It allows us, I think people tend to think of it as a lot more computing power in a centralized way, but there's this aspect of the Internet of Things of now computing power is cheap and can go everywhere, and sensors can go everywhere. And you know, from a controls perspective, this brings me back to a grad school topic, which is, when do we just throw down enough sensors that we're doing LQR instead of LQG? Because we know that LQR is robust and LQG cannot be, right? That's the famous Doyle paper, right? So, and if we actually look at the models that people use, they're fairly low order anyway. They're not, you know, really getting to all those resonances. So when do we just say, okay, I'm going to throw a bunch of sensors down here and I've got LQR now and I've got robustness? You know, it just seems like we're in that space where we need to rethink our assumptions about what has to happen as well, you know, because it's available, right? As George Carlin so cleverly said many years ago, we should do this because we can, right? You know, it's we should try putting sensors everywhere just because we can, and it makes the control system a lot simpler.
Absolutely, terrific. Kira, your comments?
Yeah. Yes, so I completely agree about the IoT and the sensing side. So I want to speak a little bit on the other aspect that Martin brought up, which is how do we think about controls and dynamic and feedback systems really advancing and continuing Moore's law. And I think one of the interesting ways that I see this is that one avenue that people are really working on is how do we create, you know, new manufacturing process capabilities, and these may be new technologies that will help to continue to push this. And in my experience, you know, these new technologies and processes, you know, they're developed at a lab scale, right? And they're research oriented, but to really have them have an impact and to be able to, you know, translate into something that's going to continue to push the envelope, you have to have the control and the system, you know, integration in there. And you have to be able to do the system identification and really take these technologies and take them out of a lab environment and push them towards what they are capable of doing. And I think that is where you can really see our field bringing this capability to the ability to try to advance and continue Moore's law.
Yeah, that's a very good point. In fact, a lot of these technologies, often they make assumptions that these things have to operate in silos. And what you're talking about in terms of systems integration, so many of the problems are actually at the interface, and controls can focus on that and bring them together. I mean, that's a great point. Angelica, I was wondering what your thoughts are.
Yes, I would like to bring in, again, a different view on this. So I thought actually that Moore's law, of course, opened a lot of room actually for additional computational resources. And this, of course, allows us to combine actually algorithms that we know from control theory with algorithms that come more from computer science, so from the machine learning perspective. And so to come up also with data-driven algorithms, but to also, let's say, challenge or keep up with the challenge that we face then, namely that we have algorithms in place where we have to guarantee convergence, where we have to guarantee safety, as we touched just before. And I think these are all new topics actually that will allow the control field to advance, but also the machine learning field to advance and to move together towards a future direction of new algorithms.
Absolutely, totally. All right, I think I'd like to move on to question 4. We can always come back and have more discussions on it. But I think there are a couple of other things that Martin brought up, and both are really very interesting. And I'd like to open it up to the whole panel. So Martin talked about University 4.0, as you all heard. And so if this is a sort of a Silicon Valley model, like people want to figure out that, okay, from school you then go to a startup mode and then figure out, and maybe there's an opportunity to come back to graduate school. So there are many different moving parts, and Martin presented some very interesting templates as to how these things need to be moved around in order to make it better. So the question is, what parts of the model are essential and what parts should be revamped? So Danny, let me start with you. What is your take on University 4.0?
It's a great holistic view of what the university can be. But I think we already see that, the funding model is different in Europe than it is in the United States for the universities. And how do you achieve, there are these fundamental questions about what does the funding model look like? What do the social implications do? If we're at a company, companies tend to invest so that they can gain a technical advantage, right? And so when you go to this safe house type university where all the research is going to be open and available to your competitors, is it, you're asking for, and it's a good thing, by the way, altruism from the company to say, I want to advance, I want some people that work for us to advance the state of the art so that the ecosystem is better. But that doesn't always, it's an interesting thing. How do you get good behavior out of everybody? And then the other thing that I see, and we see this a lot in Silicon Valley, is yes, Google gets started by a couple of Stanford graduate students who never go back to school, and that's a good thing, right? Facebook gets started by a Harvard dropout who maybe that's not such a good thing, right? It's this thing where I think that was Monday's talk, right? Monday's plenary about maybe we need to look at more than one example to see is it a good thing that graduate students leave and do startups and never come back? Or do we want that continuity? And how do we make an ecosystem where that all works? I don't have the answers. It's just those are the questions that come up to me.
Very, very good points. Kira, your thoughts?
Yeah, so I definitely agree on the funding side of things. I think funding is an area where it starts to lead to directions on how you approach a problem in some cases. But I think there's another interesting aspect that, in thinking about this, I like the University 4.0 concept. I think that that's a really nice way of thinking about bringing, sort of expertise and innovation and trying to sort of think outside the box. One thing I think that would be really important in doing that is to think about how value is going to be assigned or evaluated. And I bring that up because I think that companies and academia and entrepreneurs, they will have different definitions of what value means. And so value can mean money, right? It can simply mean what are you from a money generation perspective, what do you have? In academia, that's not That's not our currency, right? Our currency is publications and recognition for work. And then, as Danny pointed out, from a company standpoint, IP and ownership of that, knowledge is in, and also the employees, right? So that part of it. So I think that's an interesting part that has to be sort of figured out and probably always evolving. But how do those come together so that everybody is working towards a common, some type of common objective where the value that is important to each of these entities, somehow gets into that picture.
Very excellent points. So Martin, I know that you probably have some thoughts on responding. Either if you want to respond to Kira right now, we could, or maybe we could collect all of the other questions and then you can respond at the end, perhaps.
Yeah, it's perfect that Angelica goes first. I'm looking
Okay,
forward
all
also
right.
to her opinion. Yeah.
So Angelica, please weigh in. What do you think? University 4.0, thumbs up or down?
Yeah, I think we had some very good points already being said. So what I liked also from Danny, that he kind of pointed out, let's say, the lifelong learning thing, because so far universities are one in a lifetime thing, so, but I think I pretty much would like to see University 4.0 as, let's say, something that accompanies you a lifelong, actually. So you're coming back, you're getting some new knowledge, you're bringing in new knowledge and so on. So this is kind of a cycle, that closes itself a lifelong. And then I think what we also have to see is this disruptiveness. Let's say, I think Martin talked about it in terms of the management. And I think what would be key is actually to identify what could be, disruptive directions. So how should these management, or the replacement of the management who should become disruptors, identify these kind of new directions of research they want to promote, and they want to invest actually in terms of funding. So we are back actually to the problem of funding, actually Kira pointed to, and also Dani. And then I think one last thing that I wanted to emphasize is that we also have to look at the time span, actually, when, the results should become, let's say, available for the larger society and so on. So is it that we're looking at something, that is just 5 years ahead, or 10 years ahead, or 15 years ahead? And I think this is something that we also need to keep in mind, that there may be research with different time spans, actually, but still deserves funding at a certain point in time, so that even in 15 or 20 years, we have something to build on that has been investigated earlier.
Absolutely. So in fact, I'd like to add one more thing, and then I'd like to hear Martin's thoughts on all of this. I completely agree that there are two different deliverables, perhaps. One from the startup side, which is basically product and of course revenue, and from the academic side, dissemination of knowledge in the form of publications. But there is a common bridge between both of them, which is just, innovation. We want to innovate, and we want to advance the state of knowledge in science and technology, and that is common to both. But one of the difficulties in making this innovation happen is what Angelica very rightly pointed out, as to how do you figure out, the timescales are different, and for each timescale, the kind of training that is needed and the kind of knowledge base that has to be built up needs to continually be revised. And that's the challenge in figuring out when should that happen. And the two paths perhaps may be somewhat divergent. So how do you address those commonalities and distinctions, and how do we move? I think we all agree that University 4.0 is a great thing, but the question is, how do we realize it? So your thoughts, Martin?
Yeah, very nice inputs of you all. In fact, I do not agree too much that it would be essentially a Silicon Valley model, because what I try to show is that we should stop thinking inside out. So the university as a generator of startups is not the only thing we want to do. So this lifelong learning aspect is crucial, to get the people who are 10 years working in industry, to get them back into what I call the Eindhoven engine. But having said that, just as a starter, I think what is very nice is what you mentioned, Anu, is the diversity. I think one of the great things I really appreciate in working in a university is that we are so diverse, basically. Diverse in terms of time scales. In terms of time scales, diversity, in terms of sort of people. Some people you should not bother with multidisciplinary research. Just put them in a room and let them publish and think, and they will be the Nobel Prize winners in 10 or 15 years from now. And we need them. But that's not all of us. So diversity is a great thing, and we should foster that. We should really foster that. However, there's a big part where I think, I mean, we are sort of ready, I think, with focusing on the Hirsch Index. We all know this. We are now going for impact. And that's also what Anu states. Startups and scientists, they have the same thing. They want to have impact. And of course, via the money and the funding stream, that's one thing too, but that's the how, that's not the why. The why is that we want to solve the real societal problems like Corona stuff or climate or sustainability or healthcare in a broader sense. And I think working on that is binding everybody then. Now let me give you a small motivational thing which happened to us in our region 10 years ago with the financial crisis. In 2008, in 1 week, we had the financial crisis, and our truck manufacturer DAF Trucks, they lost 60% of their order intake in 1 week. So they were very nervous that they had to lay off about 100 people who were all well educated. We called them knowledge workers, so highly skilled people, and they were very nervous. They had to lay them off. And the same hold at that time for ASML and Philips and NXP, all those companies nearby. And we came up with the plan. We call it the knowledge workers arrangement, that the government would not pay the unemployment money to the people. No, they would pay a certain amount of that money to the companies, so that the companies would not have to lay off those knowledge workers, but as a counter action, the knowledge workers from the companies, they were asked to come down and to sit inside the knowledge institutes for a year or 1.5 years on a project. And in that period, in 2009 and 10, I had 10 people from DAF Trucks sitting in my lab for 1.5 years, working together with my scientists, and together they developed the first hybrid truck, so battery electric and combustion engine. And it was great for those people who were working for already 10 years in DAF Trucks, that they finally could read some papers again. And my scientists, they were really enlightened by all the practical insights of those people with that huge experience. And it was a great experience. And since that time, there is still one of the former PhD students who was working at DAF and in our lab. He is still 1 day a week working in our group from DAF. So that learned me that this lifelong learning aspect can be really utilized to make common projects together, where you get a better focus for the scientists and where you revitalize the people in industry. So this is just one aspect to mention, which I want to implement in this Eindhoven engine, because my conclusion was very soon when I was thinking about this, I cannot implement this that easy in the university. I should make something separate. And a last point, and then I will stop talking. In fact, in 2016, I was in Silicon Valley. I was invited by Singularity University to make the first chapter of the Singularity U in the Benelux, and we, with a group of 7 people, we were in Silicon Valley. And I asked the people there of Singularity U, what do you think about the future of the university? And they said, well, there's no future. I said, huh? And they said, well, the key thing is of the universities that education will be online, And all the new things will come from startups, not from universities. So your role as a university, all universities, your role is only to generate young people. That's it. And I was so angry because I was already 15 years working with industry doing innovative things. So I went back to the Netherlands, and in the plane I wrote my first blog about University 4.0 because I was so angry, and I was not accepting that our role at the university would not be bigger than this. So this is the motivation why I started this thinking about University 4.0.
Completely agree with you. The best way to innovate is to pick a small, very compelling example, show that it succeeds, and everybody will follow. Absolutely.
Yeah.
So the very last question that I'd like to end this panel with, and we have 4 minutes left. So if everybody can take less than a minute and say, what do you think is the way we can accelerate the impact of systems and control? Danny, go.
Well, and this is, preview of my talk in a month, but we need to be out there, right? It does no good to interact with practicing engineers and give them, pages of equations, and then they show you their PID controller, and you have no idea how to make measurements and no idea how to help them solve their problem. At that point, they will not talk to us again, right? So we need to be out there working with the physical problems and applying, bridging that gap between why doesn't this thing work and what is all this stuff that I learned before and I've been writing papers about, how do I make them meet in the middle?
Thank you. Kira.
Thank you. I think we need to be working on the large human-centric multidisciplinary projects. And I think when we combine together and think about work, not just from the engineering and the control side, but we bring in the social sciences, and we bring in, the ethics, and we bring in all these different fields together, that convergence is how I think we're going to have a big impact.
Thank you. Angelica.
Yeah, I think we need to work a little bit on how we communicate also systems and control to beat the larger society, but also, let's say, the really trained technicians and so on. So because, as Danny said, if we are approaching them with a long list of questions, they will probably not listen to us. So we need to find a language somewhere in between, let's say, all these equations and the practical application, so that they can understand, where this technology or where this theory brings a benefit for their application.
Thank you. Martin,
Yeah,
you have the last word.
Yes, I agree with all three what they said, all the panelists, and thank you again for being here. Thank you, Anu, for moderating. My last statement would be, please, all faculty of all universities, think about all your past PhD students who are now working in the industry, your former PhD students, when they are working in industry, make a digital network with them and revitalize them with your thoughts and start a discussion with them. And I think the impact of system and control can be much greater if you utilize your former PhD students and maybe even your former MSc students also.
Wonderful. So there you have it, ladies and gentlemen. Communicate, collaborate, network. Don't always rely on equations, and make yourself heard, and let's spread the word of systems and control and accelerate its impact. Thank you all so much for participating in this panel. I learned a lot. And again, Martin, wonderful to see your toys and the vision that you brought to this whole, to your plenary and to this panel. Kira, Danny, Angelica, thank you all again. Ladies and gentlemen, thank you all for listening and participating, and do direct your questions to us or to the Ifac organizers, and we'll be happy to continue this dialogue. Thank you all.